Welcome to the deep dive. Today, we're really getting into something foundational, the big interconnected systems that shape our world. Everything from the rocks under our feet to the atmosphere way above us.
And everything in between: energy, water, farming, the oceans.
Exactly. And us, the human population, right in the middle of it all.
Right. And you, our listener, you've given us a fantastic set of sources. So our job really is to pull out the most vital insights.
Yeah, connect the dots without making it overwhelming. We're aiming for those aha moments, that solid understanding of how it all fits together.
Precisely. We want to light up those connections between things that might seem separate.
So think of this as your guided tour to a richer understanding. We'll kick off with the literal bedrock rocks and minerals. What are they, and importantly, what happens when we try to get them out?
Good place to start.
Then we'll navigate energy, its sources, the environmental side effects. After that, water, agriculture, the oceans, the atmosphere, and finally, where we fit in. Okay, let's unpack this, starting right at the ground level.
Okay, so the sources really emphasize that rocks aren't static. They're part of this constant cycle.
The rock cycle, yeah.
Exactly. You got igneous rocks, first born from cooling molten rock, magma underground, or lava on the surface.
Like basalt.
Yeah, basalt's a great example. Cools fast when it erupts, so you get these tiny, fine-grained crystals, almost like a natural quick-setting cement.
Okay.
Then you contrast that with something like granite. It cools really slowly deep down.
Ah, so it has time to form those big speckled crystals we see in countertop.
Precisely. Big interlocking crystals, super strong. Then you have sedimentary rocks.
Limestone, sandstone.
Right, limestone, sandstone, shale. They're formed from bits and pieces, sediments piling up and getting squeezed together. Could be bits of other rocks or even shells and skeletons.
Well, that's where you might find fossils.
Exactly. Trapped in the layers,
Yeah.
like a little snapshot of ancient life. And finally, there are metamorphic rocks.
Marble, slate,
Yeah.
those ones.
They start as other rocks, igneous or sedimentary, but then they get changed. Intense heat, intense pressure, deep inside the earth. They basically recrystallize into something new.
Fascinating. So, okay, we need these materials. How do we actually find them? It's not like tripping over a gold nugget, right?
Rarely. No, it involves a lot of science and tech. Prospecting, the old school physical search still happens.
Sure.
But nowadays, we heavily rely on remote sensing, aerial photos, and especially satellites. They can cover huge areas.
How do satellites help find rocks?
Well, different minerals reflect sunlight differently across the whole spectrum. It's like they have unique fingerprints. Satellites can pick these up even through clouds sometimes. It's incredibly efficient and cost-effective for initial surveys.
Wow, okay. What else?
Geochemical analysis, that means testing samples from streams, soil, maybe shallow drilling.
Looking for chemical clues?
Exactly. High concentrations of certain elements. And GPS lets us pinpoint those spots precisely. Then there's geophysics, using seismic waves, kind of like mini earthquakes, to map out what the rock layers look like underground. Helps identify structures that might hold deposits.
Okay, so we found a promising spot using all this tech. How do we get the stuff out?
Right, extraction. It basically falls into two main camps: surface mining and subsurface mining.
Surface mining, like those huge open pits.
Exactly. Open pit mining is for deposits near the surface. You clear the land, then use explosives and massive machines to dig down in steps or benches. Some are just enormous. Quarries for sand, gravel, stone. They're a type of open pit.
And strip mining.
That's usually for things in seams, like coal. You remove the overlying rock and soil the overburden in long strips to get at the seam underneath.
Okay, and subsurface, that's for deeper stuff.
Yes. You have to sink a vertical shaft down, sometimes really deep. Then you tunnel horizontally to reach the ore.
Sounds complex.
It is. And you end up bringing a lot of waste rock to the surface, which creates those big heaps you sometimes see near old mines. And that waste needs careful management.
It sounds like a massive undertaking. Deciding to actually mine somewhere must involve a lot of factors.
Oh, absolutely. Cost is huge.
Right.
Not just exploring, but the actual cost to ton to get the ore out.
Is open pit cheaper?
Generally, yes, the per ton cost is lower because you can use bigger machines. But if the deposit is very deep, even if it's high value, shaft mining might be the only way, despite higher costs.
And the geology itself must matter.
Crucial. Is it high grade, ore, meaning lots of the valuable mineral, or low grade? Even a small deposit can be worth it if the grade is exceptional.
Makes sense. What else?
Accessibility.
Yeah.
How easy is it to get the ore out and transport it? Transport costs can be a deal breaker. Sometimes they do some basic processing right at the mine to reduce the bulk.
Right. And environmental impact. Is that a bigger factor now?
Increasingly so, yes, often legally required. Companies need plans to minimize damage, especially habitat loss, and crucially, to restore the land afterwards.
And just basic economics, I guess. Supply and demand.
Always. Metal prices go up and down.
Yeah.
A deposit that wasn't worth mining 5 years ago might suddenly become profitable if the price spikes. Or the reverse can happen.
It's a real balancing act. But what about the wider impacts? Beyond the mine site itself, what are the consequences?
They ripple outwards, ecologically and economically. Ecologically, the most obvious is habitat loss. Clearing land, building roads, it fragments ecosystems, displaces wildlife.
And pollution must be a concern.
Definitely. Noise from blasting and machinery. Water pollution is a big one. You mentioned acid mine drainage earlier. That's a classic example. Toxic metals can leach into water.
And that gets into the food chain.
It can, through bioaccumulation in organisms, and then biomagnification as it moves up the chain. Then there's land pollution from the waste heaps, air pollution from dust.
Dust can affect plants too, right? Blocking sunlight.
Yes, it reduces photosynthesis. Plus, visual pollution changing the landscape dramatically. And managing all that waste rock is a massive challenge.
It does paint a pretty stark environmental picture. Are there economic upsides?
There certainly can be. Mining creates jobs directly in the mine, but also in transport, equipment supply, refining.
Build off industries.
Exactly. For a country, it can bring in significant income, maybe foreign currency, through exports. And the money generated can sometimes fund infrastructure, roads, schools, hospitals, community building potentially.
So potential benefits, but those environmental costs sound pretty heavy. How do we manage those? What can be done to lessen the impact?
Managing the impacts is key. Safe disposal of waste is number one, designing storage that won't collapse or leak into water, and monitoring it.
And afterwards, restoring the land.
Land restoration, yes. That might involve improving the soil, maybe adding fertilizers, definitely planting trees to try and recreate an ecosystem. Sometimes bioremediation is used.
What's that?
Using living things, microorganisms, or specific plants to clean up pollutants in the soil or water. You can do it on-site, in situ, or remove the contaminated stuff and treat it elsewhere, ex situ.
Interesting. Any other uses for old mine sites?
Some, if they're stable and lined properly, can become lakes for recreation or water storage, or natural reserves. Sometimes they're even used as landfill sites, carefully managed sanitary landfills.
Okay. Looking ahead, how do we make using these resources more sustainable?
It's really twofold. We need to get better at extraction, more efficient. Maybe reprocessing old waste piles with new tech, using chemical or biological methods, improving machinery, using data better.
And using less in the first place.
Exactly. Usage efficiency, engineering things to use less material, and recycling is absolutely vital.
Why is recycling so much better?
It uses way less energy than making metals from raw ore. Much less waste, fewer emissions. And legislation has a role too, making manufacturers responsible for recycling their products, setting standards.
Right. That covers the materials that make up the planet. Now let's switch gears to the energy that powers everything. The sources get into where energy comes from and its environmental ties.
Yeah, fossil fuels, coal, oil, natural gas. The sources remind us they're basically ancient sunlight, stored over millions of years.
From dead plants and animals, right?
Pretty much. Coal, mostly from ancient swampy forests, plants, and peat, buried and compressed. Oil and gas, generally from tiny marine creatures buried under ocean sediments, cooked by heat and pressure over eons.
Millions of years to form.
And we're burning through them relatively quickly. That contrast is stark.
And our demand for energy just keeps climbing, doesn't it?
It really does.
Yeah.
Global demand is rising steadily. Key drivers are population growth, industrialization, more people moving to cities, and generally rising living standards, meaning higher energy use per person.
So where do we actually get all this energy? The sources mentioned quite a few.
We can split them into non-renewable and renewable, broadly speaking.
Non-renewable meaning they run out.
Essentially, yes. Fossil fuels are the main ones. Nuclear power, too, since it uses uranium, which is finite. They formed over geological time and aren't replaced quickly.
Okay. And renewables?
They replenish naturally on a human timescale. Things like geothermal heat from the Earth's core, hydroelectric from flowing water, tidal and wave power from the oceans, wind power, solar energy from the sun, and biofuels.
Biofuels, like ethanol from corn.
That's one type. Also biogas from digesting waste or biodiesel from plant oils. Their sustainability can vary a bit depending on how they're produced, especially land use.
Okay, so we have all these different sources. How do we turn them into the electricity we actually use?
For most large-scale generation, the core idea involves turbines and generators.
Turbines, like big fans.
Sort of. Blades that get turned by something moving could be steam, water, wind. That spinning motion turns a generator, which uses magnets and wires to create electricity.
So how does that work for different sources, fossil fuels?
You burn them to heat water, make high-pressure steam, and that steam spins the turbine. Nuclear power uses heat from nuclear fission, splitting atoms, to do the same thing, make steam.
Okay. What about renewables? Geothermal.
Geothermal taps into underground hot water or steam directly to spin the turbine. Wind turbines are obvious. The wind spins the blades connected to the generator.
And solar. That's different, right? No turbine.
Right. Solar photovoltaic panels convert sunlight directly into electricity using semiconductor materials. No moving parts in the panel itself.
Interesting. What about ocean power?
Tidal power often uses barrages, like dams across estuaries, letting water flow through turbines as the tide comes in and out. Wave power uses various devices to capture the wave motion and turn a generator. And hydroelectric uses dams to store water high up, then lets it flow down through turbines.
So it sounds like every method has its pros and cons.
Absolutely. Fossil fuels. Historically abundant, the tech is well known. But big downsides. CO2 emissions driving climate change, air pollution, and they are finite.
And biofuels. They're renewable,
But they can take up a lot of land, sometimes competing with food crops or causing deforestation. And burning them still produces some pollutants, though plants absorb CO2 as they grow.
when we look at how much energy we use, what drives that demand? It's not just population, is it?
No, it's complex. In our homes, affordability matters. Cheap energy encourages use, availability, even social status, having latest gadgets. Think about wanting strawberries in winter that takes energy for greenhouses or transport.
And industry.
Big user. Manufacturing, especially metals, cement. And as luxury goods become cheaper, we make more of them, using more energy. Transportation is huge, too. Global supply chains rely almost entirely on fossil fuels for ships, trucks, planes.
Wealth must play a part, too.
Definitely. Economic growth usually means more energy use. Recessions often see a dip. And climate, of course, heating in cold places, air conditioning in hot places, lighting everywhere. Climate change itself is boosting demand for cooling.
So demand is rising, environmental concerns are serious. What can we actually do to manage our energy use better? Conserve it.
Conservation and efficiency are key. Reducing how much we use overall is the first step. Better insulation in buildings is a big one. Less heating and cooling needed.
Simple things like turning off lights.
Absolutely. Switching off devices. Choosing energy-efficient appliances. Sometimes governments have scrappage schemes to encourage replacing old, inefficient cars or boilers.
What about generating energy more efficiently? Or from waste?
Yes, using efficient tech like LED lights makes a difference. And energy from waste is promising. Anaerobic digestion, breaking down organic waste without oxygen, produces biogas you can burn.
Like from food scraps.
Exactly, or farm manure. You can also incinerate waste to generate electricity, but you have to manage the emissions and ash carefully. And recycling used cooking oil into biodiesel is another route.
Does public awareness help?
Hugely. Educating people about the benefits, energy ratings on appliances, and government regulations are vital. Stricter building codes, banning really inefficient products, offering incentives for efficiency.
And using more renewables.
Maximizing renewables is crucial. Maybe keeping some fossil fuel plants for backup when the sun isn't shining or the wind isn't blowing. Transport policies are important too. Better public transport, cycle lanes, vehicle emission standards, cleaner fuel incentives.
What about things like fracking? That's mentioned as a way to get more gas.
Right, fracking, hydraulic fracturing, aims to get oil and gas trapped in shale rock. You inject high-pressure water, sand, and chemicals to fracture the rock and release the fuel.
What are the pros and cons there?
Well, proponents point to increased domestic energy supply, maybe energy independence, job creation. But the disadvantages are significant and well documented. Risks of groundwater contamination from the fluids or escaping gas, the sheer volume of water used, potential links to small earthquakes, noise pollution, local environmental damage. It's highly controversial.
A lot to weigh up there. Okay, energy is critical, but so is water. Let's pivot to that. The sources get into where water is found and the challenges in managing it.
First thing the sources stress is how unevenly water is distributed. About 97% of all Earth's water is salty ocean water.
Only 3% fresh water?
Roughly, yes. And of that 3%, something like 2/3 is locked up in ice caps and glaciers. So the amount of readily available liquid freshwater is surprisingly small.
Wow. And where does that fresh water come from? How does it move around? The water cycle.
Exactly, the water cycle. Precipitation rain, snow brings water down from the atmosphere. On the ground, it can run off the surface into rivers and lakes.
Or soak in.
Right, interception by plants first, then infiltration into the soil. It can flow through the upper soil layers, that's through flow, or seep deeper down into groundwater.
And it gets back into the air how?
Evaporation from surfaces like lakes and rivers, and transpiration from plants releasing water vapor. That vapor condenses into clouds, and the cycle starts again.
So given that cycle, how do we actually get the water we need for everything?
We tap into different sources. Surface water, rivers, lakes, wetlands is the most obvious from many places.
And underground? Wells.
Yes. Wells access groundwater stored in the soil and rock layers. Aquifers are important layers of permeable rock that hold and transmit a lot of water. Some are artesian, meaning the water's under pressure and rises naturally.
What about reservoirs?
Reservoirs are artificial lakes made by damming rivers. They're vital for storing water, controlling floods, sometimes generating power. You also have smaller service reservoirs like water towers to store treated water and maintain pressure.
And desalination, making fresh water from seawater.
That's becoming more common in dry regions. Two main methods. Distillation, basically boiling the water and condensing the steam, which uses a lot of energy.
And leaves salty brine behind.
Yes. The other is reverse osmosis, forcing water through membranes under pressure. More energy efficient, usually.
What are the drawbacks of desalination? It sounds like a great solution.
Well, it's expensive to build and run, very energy intensive, often relying on fossil fuels, ironically. Access can be an issue if you're inland. It needs skilled workers. And disposing of that concentrated brine byproduct can harm marine life. But it does offer a potentially huge, drought-proof supply for coastal areas.
So once we get the water, where does it all go? What do we use it for?
Broadly, domestic, industrial, and agricultural use. Domestically, drinking and cooking is a small part. Most goes to flushing toilets, washing ourselves and clothes, watering gardens, washing cars. And leaks in the system lose a fair bit too.
Industry must use a lot.
Huge amounts. Cooling in power plants and factories is a major one. Using it as a solvent for mixing things, making steam.
And farming.
Agriculture is the biggest user globally by far, mostly for irrigation to grow crops, plus drinking water for livestock.
It seems obvious access must vary hugely around the world. Water-rich versus water-poor countries.
Definitely. Some places have lots of rain, big rivers. Others are deserts or small islands. But it's not always simple. Big countries can have dry regions. And technology can help overcome natural limits sometimes.
Can lack of water lead to conflict?
Sadly, yes, in some regions. It's also important to distinguish physical scarcity. Just not enough water from economic scarcity.
What's economic scarcity?
That's where the water might be there, but people lack the money or infrastructure to access it safely. You often see urban areas having better access than rural ones because of investment and political clout.
The sources mentioned multi-purpose dams, like the Ramganga Dam. What's involved in projects like that?
They're massive engineering projects designed for several benefits at once. Choosing the site is critical. You look at rainfall, temperature, the geology is the rock stable, elevation for power generation, valley shape for storage.
Yeah.
Is it near people? Easy to get to for construction.
What are the typical benefits?
Generating hydroelectricity, which is renewable. Controlling floods downstream. Providing water for irrigation. Boosting farming. Creating a reservoir for recreation, maybe fishing. Reliable drinking water supply. Sometimes creating new habitats. Maybe improving river navigation. Jobs during construction and operation. Water storage.
Sounds great, but there must be downsides too.
Oh, significant ones. People living in the valley have to be relocated. Valuable land, maybe farmland or forests, gets flooded. Dams block fish migration. Sediment builds up behind the dam, reducing its lifespan and effectiveness.
And cost.
Very high construction costs, plus ongoing maintenance. And downstream impacts changing river flow affects ecosystems, fisheries, maybe reduces natural soil enrichment from floods. Sustainability is a big debate. Renewable power versus ecological damage and limited lifespan.
Let's talk about water pollution. What are the main culprits?
Comes from many sources. Sewage is a big one. Organic waste, pathogens, nutrients like nitrates and phosphates, especially where sanitation is poor.
What else? Household waste.
Yes, detergents, Chemicals wash down drains. Industrial processes release all sorts of chemicals, heavy metals. Even air pollution contributes through acid rain.
And farming again.
Agriculture is a major source runoff, carries excess fertilizers, manure, pesticides, those agrochemicals into rivers and groundwater.
What are the consequences of all this pollution?
They're severe. Big inequalities globally in access to clean water. Waterborne diseases like typhoid and cholera are still huge problems where water is contaminated.
And for aquatic life.
Toxic chemicals can kill fish directly or reduce oxygen levels. Then there's bioaccumulation and biomagnification we talked about earlier. Acid rain lowers the pH of water, harms fish reproduction, leaches toxic aluminum from soils.
And eutrophication, that's from fertilizers, right?
Primarily, yes, nutrients from fertilizers and sewage. It causes excessive algae growth, algal blooms. When the algae die and decompose, the bacteria use up all the oxygen in the water, creating dead zones where nothing much can live.
So faced with all this, how do we manage water pollution?
Needs multiple approaches. Better sanitation is fundamental, proper sewer systems, septic tanks, safe toilets. Sewage treatment plants are crucial.
How do they work, basically?
They use physical processes like screening out large objects, letting grit settle, then biological processes, sludge settling, and digestion using microbes, which can even produce biogas. Aeration adds oxygen. Finally, disinfection, often with chlorine or UV light, kills pathogens.
And controlling pollution at the source.
Essential. Regulations on industrial discharges, setting pollution limits, monitoring water quality, finding polluters. International agreements are needed for shared rivers or lakes.
What about managing water-related diseases?
For waterborne diseases like cholera, it's about clean water, sanitation, treatment, hygiene. For water-bred diseases like malaria, where mosquitoes breed in water, it's about controlling the mosquito nets, draining stagnant water, larvicides, education.
Water is clearly vital and under pressure.
Yeah.
Okay, let's move on to agriculture feeding everyone and how that interacts with the environment.
Right, and it starts with soil. The sources describe soil as this mix of mineral particles, sand, silt, clay, plus organic matter, air, and water.
And the mix varies a lot.
Hugely. Depends on the original rock, climate, landscape, living organisms, time, and how humans manage it. The particle size really defines the texture. Sand feels gritty, silt, silky, clay sticky.
And what does soil actually do for plants?
Several key things. It holds and supplies essential mineral ions. Nitrogen is nitrate, phosphorus is phosphate, potassium ions. Plants need these to grow.
And the organic stuff.
Humus.
Yes, humus comes from decomposed plants and animals, broken down by earthworms, fungi, bacteria. It's vital for good soil structure, holding water, allowing air in, improving drainage, and holding on to those nutrients.
Other important soil properties.
pH acidity or alkalinity affects which nutrients plants can actually absorb. Drainage is key. Plants don't like waterlogged roots. How easy it is to cultivate. Sand, silt, and clay soils behave very differently in all these aspects.
We see different kinds of farming around the world. How are they categorized? Big distinction is subsistence versus commercial. Subsistence is mainly growing food for your own family, maybe a tiny bit to sell. Commercial is growing crops or raising animals primarily for sale, usually on a larger scale.
And arable versus pastoral.
Arable is growing crops. Pastoral is raising livestock like cattle or sheep. Mixed farming does both.
Okay. Now, farmers need to produce more and more food. What techniques do they use to increase yields?
Lots of techniques. Crop rotation is a big one, planting different types of crops in sequence on the same field.
Why do that?
Helps maintain soil fertility. Legumes add nitrogen, for example. It also breaks pest and disease cycles, helps control weeds. You might have a sequence like legumes, then leafy greens, then root crops, then maybe let the field rest. Fallow.
Fertilizers must be key too.
Definitely. Adding nutrients plants need. You have organic fertilizers, manure, compost, and inorganic or synthetic chemical fertilizers.
What's the difference in practice?
They differ in how easy they are to store and apply, how concentrated the nutrients are, how quickly they release nutrients, their effect on long-term soil health, cost, and safety considerations.
Irrigation. Adding water.
Crucial where rainfall isn't enough. Different methods exist: overhead sprinklers, clay pots buried in the soil releasing water slowly, trickle or drip irrigation directly to the roots, very efficient, and flood irrigation covering the whole field. Each has pros and cons for water use, cost, suitability.
What about pests and weeds?
Pest control uses pesticides, chemicals like fungicides and insecticides. Biological control uses natural enemies of the pests. Herbicides target weeds. Cultural controls are things like hand weeding or using barriers.
And machinery? Tractors and combines.
Mechanization allows farmers to work much larger areas with less labor. Selective breeding has been used for centuries, choosing the best plants or animals to breed from, gradually improving traits.
What about GMOs, genetically modified organisms?
That's altering the crop's genes directly to add desirable traits, like resistance to pests or herbicides. Can boost yields, but there are ongoing debates about potential environmental and health impacts.
And things like greenhouses.
Controlled environments, yes. Greenhouses let you manage temperature, light, humidity, even day length. Hydroponics goes further, growing plants in nutrient solutions without soil at all. Can get high yields, but can be expensive and energy intensive.
So these techniques boost yields, but do they cause problems too, environmental impacts?
Yes, many intensive methods have downsides. Overusing pesticides can lead to resistant pests, harm beneficial insects like pollinators, drift onto other areas, and leach into water.
And too much fertilizer.
That can be wasteful. Leach into waterways, causing eutrophication, that algae bloom problem again. High nitrates in drinking water can cause health issues like blue baby syndrome, can also mess up soil pH or even scorch plants.
What about irrigation issues?
Poorly managed irrigation can compact the soil, make it waterlogged, wash away nutrients, create a hard crust on the surface, or lead to salinization, a buildup of faults, especially in dry areas.
Other problems.
Overproduction can lead to waste if storage or transport is inadequate. Continuously cropping without replacing nutrients depletes the soil. Soil erosion is a huge one, and sometimes focus on cash crops for export can mean less land is used for growing basic food for local people.
Soil erosion sounds really bad. What causes it, and what are the effects?
It's the loss of topsoil, usually by wind or water. Removing vegetation is a major cause. Plants hold the soil together, overcultivation loosens it, overgrazing by animals strips vegetation and compacts the soil.
So rain and wind can just carry it away.
Exactly. Heavy rain causes runoff, especially on slopes. Wind blows dry, bears soil away. Compaction from machinery makes water run off faster. It can lead to gully erosion, deep channels being carved out.
And the impacts?
Loss of fertile topsoil means lower crop yields. Habitats for soil organisms are destroyed. Sediment clogs up rivers and lakes, which can worsen flooding and harm aquatic life. It can lead to desertification in dry areas. Ultimately, it can force people to migrate and even cause famine.
How can we stop or reduce soil erosion? What management techniques work?
Several good strategies. Terracing on slopes, creating flat steps, slows down water runoff. Contour, plowing across the slope, not down it, creates ridges that trap water.
What about physical barriers?
Bunds, small earth banks along contours hold back water. Windbreaks, rows of trees or hedges reduce wind speed across fields.
Keeping the soil covered seems important.
Crucial. Maintaining vegetation cover, maybe using cover crops like legumes between main crops. Some farmers use a no-dig approach to minimize disturbance. Adding organic matter improves soil structure and resistance to erosion. Planting trees, mixed cropping, crop rotation, they all help.
So the goal is sustainable agriculture. What does that really mean, and what does it involve?
Sustainable agriculture aims to meet our food needs now, without wrecking the ability of future generations to meet theirs. It focuses on using resources efficiently, supporting natural ecosystems, and ensuring farmers can make a living.
What kind of strategies does it use?
Things we've touched on. Using organic fertilizers to build soil health. Manage grazing to prevent damage. Crop rotation. Using crop varieties that naturally resist pests or drought. Reducing the need for chemicals or excess water. Efficient irrigation like trickle drip. Rainwater harvesting. Integrated pest management that uses a mix of methods, minimizing chemicals.
Okay, let's move from the land to the sea. Oceans and fisheries. Our sources talk about them as huge resources under pressure.
They really are. Oceans provide so much. Food, obviously fish, shellfish, chemicals and materials, salt, magnesium from seawater, but also minerals mined from the seabed like tin, diamonds, sand, gravel, though mining has impacts.
And energy. Oil.
Huge amounts of offshore oil and gas. Plus potential for wave and tidal energy. Tourism is massive, especially for coastal economies. Beaches, diving, boat trips, and transport oceans are the highways for global trade via container ships, tankers, bulk carriers.
Where do most of the fish we catch actually come from? Are they spread evenly?
Not at all. Most fishing happens on the continental shelves, those shallower areas around the continents, usually less than 150 meters deep.
Why there?
Sunlight. It can reach the bottom, allowing phytoplankton to grow. These tiny algae are the base of the marine food web. They need light, CO2, water, and nutrients like nitrogen and phosphorus. Below about 200 meters, there's not enough light for photosynthesis.
Are some areas naturally richer than others?
Yes, especially areas with upwelling. That's where deep, cold, nutrient-rich water comes to the surface. The coast of Peru is a classic example. Massive anchovy fishery fueled by upwelling. But this also leads to overfishing, taking fish out faster than they can reproduce.
The sources mention El Niño. How does that climate pattern affect fishing?
El Niño disrupts those normal patterns in the Pacific. You get warmer water off South America, and crucially, that upwelling of cold, nutrient-rich water often stops or weakens.
So no nutrients.
Means less phytoplankton, which means less food for the anchovies. The fishery can collapse during strong El Niño events, impacting everything that depends on it, like the fish meal industry that feeds farmed fish.
So exploiting the oceans, especially fishing, clearly has impacts. What are the main ones?
Overfishing is the big one. Driven by demand, powerful boats with sonar, huge nets, it leads to falling catches overall or catches staying flat despite more effort. Fish caught are often smaller on average.
And catching things you don't mean to by catch.
Huge problem. Nets often catch non-target fish, dolphins, turtles, seabirds. Many die. It reduces biodiversity, disrupts the whole ecosystem. Different net types have different impacts. Drift nets, seine nets, bottom trawls that scrape the seabed. Some are worse than others.
Is fish farming mariculture a potential solution?
It's often presented as one. Farming marine species can, in theory, reduce pressure on wild stocks. It provides a steady supply, avoids bycatch, doesn't damage the seabed like trawling.
Mariculture is marine, aquaculture is freshwater.
Generally, yes.
Yeah.
Mariculture has potential benefits, but it needs to be done responsibly. Issues like pollution from fish farms, escaped fish, and feed sources need careful management.
So how can we manage wild fisheries more sustainably? What tools do we have?
A range of tools. Gear restrictions are important in net types, mesh sizes. If the mesh is too small, you catch young fish before they breed. Square mesh panels can let small fish escape better than diamond mesh.
What else?
Species-specific methods like pole and line for tuna avoids the bycatch associated with fish aggregation devices, or FADs. Technology like sonar helps catch fish, but also fuels overfishing. Quotas limits on how much can be caught are common. Closed seasons protect fish during breeding times.
Protected areas, like parks in the sea.
Exactly. Marine protected areas or reserves where fishing is restricted or banned. International agreements are vital too because fish don't respect borders. Things like the Law of the Sea Convention set rules for economic zones and high seas fishing.
Does monitoring and enforcement work?
It's essential, but incredibly difficult. Oceans are vast. Illegal fishing happens because people need income or food. Cheating on quotas, using illegal nets, fishing in closed areas. It all happens. Some places, like Namibia, have strong monitoring with observers on boats, patrols, logbooks, but it's a constant challenge.
Okay, shifting now to managing hazards, the powerful forces of nature our planet throws at us.
Right. The sources start with Earth's structure. You've got the core, solid inner, liquid outer, mostly iron and nickel. Then the mantle, silicate rocks, where convection currents slowly move the tectonic plates above.
Those plates make up the crust, the lithosphere.
Yes, the rigid outer layer. And where these plates meet the boundaries, that's where most of the action happens.
What kinds of boundaries are there?
Constructive or divergent, where plates pull apart. In oceans, this creates new seafloor, like the Mid-Atlantic Ridge. You get volcanoes, usually shield volcanoes and earthquakes, but often smaller ones. On land, it forms rift valleys.
And then destructive, where they crash together.
Destructive or convergent. If ocean crust meets continental crust, the denser ocean plate dives under subduction, creates deep ocean trenches, big earthquakes, explosive volcanoes like Mount Fuji, and fold mountains like the Andes.
What if two ocean plates collide? Or two continents?
Ocean collision makes island arcs, like Japan. Continent collision crumples up huge mountain ranges like the Himalayas, big earthquakes, but no volcanoes usually.
And the last type?
Conservative boundaries, where plates slide past each other horizontally, like the San Andreas Fault. Lots of earthquakes, but generally no volcanoes.
Earthquakes and volcanoes, how do we measure them? Where do they happen?
Earthquake magnitude is usually measured on the Richter scale, using a seismometer. They happen mainly at plate boundaries, caused by the sudden release of energy when plates slip or break. The focus is underground. The epicenter is the point directly above on the surface.
What affects how bad an earthquake is?
Lots of things. Magnitude, obviously. Depth of the focus. Location of the epicenter, urban or rural. Time of day. The local geology, soft ground shakes more. Relief landslides on slopes. Aftershocks. How well buildings are constructed. Population density.
And volcanoes. Mostly at boundaries, too.
Mostly at destructive and constructive boundaries, yes. but also at hotspots, places like Hawaii, where magma plumes rise from deep in the mantle, away from plate edges.
Okay, what about weather hazards? Tropical cyclones.
Also called hurricanes or typhoons. They need warm ocean water, at least 27 Celsius, and deep, down to 60 meters or so. They form between about 5 and 20 degrees latitude. They need the Earth's rotation, the Coriolis effect, to spin them up, so not right on the equator. And they need low wind, shear winds at different heights blowing similarly.
And floods. What causes them?
Can be natural heavy or prolonged rain, rapid snowmelt, steep slopes concentrating water, soil already saturated, coastal flooding from storm surges or tsunamis. But human factors make them worse.
Like deforestation.
Yes, fewer trees mean more runoff. Farming down slopes can channel water. Urbanization creates impermeable surfaces, concrete, tarmac, so water can't soak in. And climate change is leading to more intense rainfall and sea level rise.
And droughts. Just lack of rain.
Primarily, yes. Often linked to persistent high-pressure systems that block rain-bearing weather. Big climate patterns like El Niño and La Niña affect rainfall patterns globally. And climate change is projected to make droughts more frequent and severe in many areas.
These hazards can cause immense damage. What are the typical impacts?
Tectonic events, quakes, volcanoes cause building collapse, fires, tsunamis, landslides, destroy farmland, habitats, contaminate water, spread disease, huge loss of life, mental health impacts, massive economic costs.
Tropical cyclones.
Intense winds, torrential rain leading to flooding and landslides, storm surges inundating coasts, widespread damage, death, disruption to power and transport, disease outbreaks, economic losses, crop destruction,
Flooding in general.
deaths, injuries, property damage, contaminated water supplies, crop and livestock losses. Can sometimes deposit fertile silt, but the damage usually outweighs that. Huge financial costs.
And droughts.
Water sources dry up, crops fail, livestock die. Wildlife suffers, land prices can fall, people might migrate, unemployment rises in farming areas, food prices increase, leading to malnutrition, even famine, increased risk of soil erosion, desertification, wildfires, can lead to conflicts over scarce water.
Given these terrible impacts, how can we manage them? Can we predict these things?
Management involves prediction, preparation, and protection. For volcanoes, prediction uses seismometers for tremors, satellites checking ground heat, GPS tracking ground swelling, analyzing gas emissions. It's getting better.
How do you protect against volcanoes?
Hazard maps show risky areas. Sometimes try building barriers to divert lava, spraying water to cool lava flows, reinforcing buildings against ash.
What about earthquakes? Prediction is harder there, right?
Much harder. Scientists look for small tremors, changes in groundwater or radon gas, patterns from past quakes, magnetic field changes, even animal behavior. But reliable short-term prediction isn't really possible yet.
So preparation and protection are key.
Absolutely. Building codes for earthquake-resistant structures are vital. Retrofitting older buildings, smart meters that shut off gas lines, land use planning, avoiding building critical infrastructure on fault lines.
Tropical cyclones. Prediction.
We're pretty good at tracking them with satellites now, giving days of warning usually.
And protection.
Building strong shelters. Coastal defenses like embankments or seawalls. Preserving natural defenses like mangrove swamps. Evacuation plans. Prediction involves monitoring rainfall and river levels closely. Protection uses hard engineering like levees, flood barriers, dams, and soft engineering like planting trees upstream to slow runoff, creating flood storage areas. Widening river channels.
What can individuals or communities do?
Land use planning is key. Don't build houses on floodplains. Sandbagging, pumps, adapting houses like raising electrical sockets.
And droughts.
Monitoring rainfall and temperature helps predict them. Preparation involves increasing water supplies, reservoirs, maybe desalination. Conservation is vital, less waste. Using drought-tolerant crops, efficient irrigation, recycling water. Reducing deforestation helps maintain water cycles. Governments can stockpile food.
Interestingly, the sources say hazards can sometimes offer opportunities. Why would people live in dangerous places?
Several reasons. Family and community ties can be very strong. People might trust the prediction and protection systems. Jobs, often in tourism, attracted by dramatic landscapes like volcanoes or coastlines. Sometimes people simply lack the resources to move.
Any other benefits?
Fertile volcanic soils are great for farming. Scenic beauty. Geothermal energy potential near volcanoes. Mineral deposits are often found in tectonically active areas. And rivers, despite flood risk, provide water, transport, fertile land.
Okay, let's move up into the atmosphere. Vital, complex, and definitely impacted by us.
Yes, the atmosphere. Sources remind us it's mostly nitrogen, about 78%. Oxygen is next, around 21%, crucial for breathing, obviously. Then small amounts of water vapor, argon, and trace gases, including carbon dioxide.
CO2 is trace, but important, right? Greenhouse gas.
Exactly. Vital for keeping the planet warm enough for life, but too much causes problems. The atmosphere has layers to troposphere near the ground where weather happens, then stratosphere with the ozone layer, mesosphere, thermosphere way up high. And different gases stick around for different lengths of time, their residence time.
And humans are changing the atmosphere. Pollution.
Significantly. Acid rain is one big issue, caused by sulfur dioxide, SO2, and nitrogen oxides, ADOX, mainly from burning fossil fuels in vehicles. They react in the air to form acids.
And smog.
That hazy air pollution can be industrial smog from burning coal or photochemical smog in sunny cities. That involves reactions with sunlight, NOx, and volatile organic compounds, VOCs, things like evaporating fuels or solvents forming ground-level ozone, which is harmful.
Temperature inversions make it worse.
Yes, they trap polluted air near the ground, especially in valleys. Then there's the enhanced greenhouse effect.
More greenhouse gas is trapping more heat.
Exactly. More CO2 from burning fossil fuels and deforestation. Methane from cattle, rice paddies, landfill coal mining, CFCs, chlorofluorocarbons from old fridges and aerosols, nitrogen oxides again, tropospheric ozone.
And CFCs also damage the other ozone, the ozone layer.
Correct. CFCs rise to the stratosphere and release chlorine, which breaks down the protective ozone layer up there.
What are the impacts of all this pollution?
Smog irritates eyes, throats, lungs, makes asthma worse. Acid rain damages lakes, forests, crops, buildings. Ozone layer depletion lets more harmful UV radiation through. More sunburn, skin cancers, cataracts can harm phytoplankton, affecting ocean food webs. And climate change from the enhanced greenhouse effect has huge impacts.
Like sea level rise?
Yes, from melting ice. More extreme weather, heat waves, floods, droughts, biodiversity loss as habitats change, coastal erosion, impacts on farming, water supplies, human health. It's extensive.
So how do we manage atmospheric pollution? What can be done?
Reducing our carbon footprint is key. Using less fossil fuels, switching to renewables, improving energy efficiency everywhere.
Can we capture the carbon?
Carbon capture and storage technologies aim to trap CO2 from power plants or factories and store it underground. Still developing and expensive, but potentially part of the solution. Transport policies are vital, shifting to cleaner vehicles, better public transport, promoting walking and cycling.
What about international efforts?
Agreements like the Montreal Protocol successfully tackled CFCs and ozone depletion. The Kyoto Protocol and Paris Agreement aim to address climate change, though challenges remain. Replacing CFCs with alternatives, safely disposing of old ones.
Other technologies.
Catalytic converters on cars cut harmful emissions. Scrubbers on power plant chimneys can remove sulfur dioxide to reduce acid rain. Planting trees, reforestation, and afforestation helps absorb CO2.
Okay, last major topic.
Right.
Us, the human population. Growth, distribution, management.
Right. Population is the number of people. Density is how crowded they are on average. Distribution is how they're spread out, often near water and resources.
What influences where people live globally?
Physical factors are big. Climate, people avoid extreme cold, heat, or dryness. Release, steep mountains are usually sparsely populated. Natural resources, fertile soils for farming.
And population growth follows a pattern.
Often described in phases. A slow lag phase, then rapid log or exponential growth, then maybe a stationary phase where growth levels off as it nears the environment's carrying capacity, the maximum population it can sustainably support.
How has human population grown historically?
Very slowly. For most of history as hunter-gatherers. Then agriculture allowed growth to speed up. It hit 1 billion around 1800, then rocketed up past 7 billion recently. The rate of growth is slowing now, but the numbers are still increasing significantly each year.
What affects birth rates and death rates?
Birth rates depend on things like infant mortality. If babies often die, people tend to have more. Farming economies might value child labor. In richer countries, kids are expensive, there are pensions, better access to contraception. Social factors, women's education play a role.
And death rates
have fallen dramatically due to better healthcare, sanitation, nutrition, living standards. Though conflict and diseases still have impacts, natural increase is just births minus deaths.
Migration changes things too.
Big time. People moving, often rural to urban in developing countries seeking work, sometimes urban to rural in developed countries seeking a different lifestyle, driven by push factors making them leave. Poverty, war, and pull factors attracting them elsewhere. Jobs, safety, population growth overall is births plus immigration minus deaths plus immigration.
We often see age pyramids showing population structure. What do they tell us?
They show the proportion of people in different age groups, split by sex. A wide base means lots of young people, typical of a rapidly growing population in a developing country, LEDC. A more rectangular shape means slow or zero growth, stationary, common in developed countries, MEDCs. A narrow base means the population might be shrinking, contracting, also seen in some MEDCs.
And they show dependent versus independent populations?
Yes. Kids under 16 and seniors over 65 are generally dependent. The working age population, roughly 1765, is independent. Taxes from the independent group support services like schools and pensions for the dependent groups. The pyramid shape really affects a country's future needs and challenges.
So, given the impacts of population size, how is it managed?
Various approaches. Family planning programs providing contraception and education are key, letting people choose their family size. Improving health and education, especially for women, generally leads to lower birth rates as women have more opportunities and infant mortality drops.
Do governments have policies?
Some do. Pronatalist policies encourage births, like in France, offering benefits for larger families. Antinatalist policies aim to slow growth, maybe promoting smaller families, or, controversially, like China's former one-child policy. Many countries have no explicit policy. Migration policies can also affect numbers. Raising the legal marriage age can have an effect too. Ultimately, parental choice, enabled by education and access to resources, is a major factor.
Wow. We have covered an incredible amount of ground today, from deep inside the Earth right out to the atmosphere, and how humanity fits into it all.
It really is amazing how linked everything is, isn't it? As the sources showed, the rocks we dig up affect energy, which impacts the atmosphere, which changes water cycles and farming, which affects us and our oceans. It's all one big system.
Yeah, human activity is the thread running through almost all of it, influencing these natural systems so powerfully.
Definitely.
I certainly had a few aha moments, really grasping the importance of soil health for everything related to agriculture and seeing the direct link between ocean currents and fish stocks. That was eye-opening.
For me, thinking about how long some of those greenhouse gases actually stay in the atmosphere, it really brings home the long-term nature of the choices we're making now about energy. Hopefully, this deep dive has given you, our listener, a more connected view of these vital Earth systems and maybe where you fit within them.
Absolutely. So as you think back on our conversation, here's something to ponder. Considering the limits of many resources and the clear signs of environmental change, where do you think the biggest opportunities are for building a more sustainable path forward? Is it changing how we get and use materials? Revolutionizing energy, managing water better, shifting agriculture, protecting oceans and air, or thinking differently about population growth? A big question with huge implications for our collective future, something to definitely explore further.